get started. All right, and so Oliver, part 2 of his lectures on the motivic slice spectral sequence.
Okay, thanks a lot, Dan. So, if you have any questions, just interrupt me. My plan is to...
Yeah, and let me endorse that suggestion that, you know, one of the things we have to learn to do in this online format is be a little bit aggressive. If we do have questions, we just kind of have to force our way. Did you just see how I just interrupted him just now, right? Don't hesitate to just interrupt. That's just kind of what that's just what has to be done. Okay, thanks.
Yeah. Here's a short recollection on the filtrations I defined, and they were in some sense all defined in the same manner. So you take some set, for example, some kind of suspensions of smooth schemes, and then you look at the full subcategory closed under homotopic limits and extensions, which contains this set. So for a fixed integer q, we have the q connective subcategory, the Q connective motivic spectra, where you let the weight wander through all the integers. And you have the Q effective subcategory, where you let the simplicial suspension walk through all the integers. But the weight is fixed now. And you have the very Q effective motivic spectra, where there's no integer wandering around. It's just the smooth schemes that sort of index this. This gives 3 different filtrations. You can, by definition, see that a very Q-effective motivic spectrum is both Q-effective and also Q-connective. And I listed some of the properties I emphasized last time. So the Blavatsky slice filtration, the effective filtration, is not a Hausdorff filtration, but it is a triangulated one. Here are sort of 2 examples of interesting motivic spectra. So the Q-fold simplicial suspension of the eta inverted sphere. This is not L effective for any L, but it's Q connective. And this spectrum representing étale cohomology with mod 2 coefficients is Q effective for all Q and not Q connective for any Q. So this shows the not Hausdorff property, for example. And here's the notation for sort of the Qth cover for each of these filtrations, the Qth connective cover, the Qth effective cover, and the very Qth effective cover. It's always a bit awkward to pronounce this, and well, my apologies. And then we have sort of the slices. There's some short notation for Blavatsky slices and the Spitzweck's very effective slices. And for the sort of homotopy T structure, you can think of the slices as the Allenbeck-MacLane spectra with respect to the corresponding homotopy module. Okay, these are the filtrations, and this is then the setup. Let's stick now to the effective filtration, Blavatsky slice filtration. Then we get this spectral sequence, and we're not sure whether it converges to this exhaustive filtration that you get on the homotopic groups. And of course, if you like, you do not have to restrict to homotopic groups. You can map any motivic spectrum to the slices and ask whether this will converge. This is usually done where D is the suspension spectrum of some smooth scheme. And yeah, the first differential for the slice spectral sequence is given by this composition of canonical maps from the Q slice to the simplicial suspension of the Q plus first filtration to the Q plus suspension of the Q plus first slice. And if you look at what the first differential does on homotopic groups, you get this sort of shift in the simplicial degree. And just because this comes from some map of motivic spectra, it has to be a module homomorphism with respect to Milnor-Witt K-theory. So this is nothing specific about the slices at all, but there's going to, so something will happen for the slices. We will see soon what the zero slice of the sphere is, and this will imply that, in fact, all the differentials in the slice spectral sequence are actually Milnor K-theory module homomorphisms. And this will turn out to be very convenient sometimes. Okay, so let's try to determine some slices, and let me start with the motivating example of algebraic K-theory. This is the theorem, which I guess was it was proved by Mark Levine using his homotopy coniveau filtration, and sort of it was suggested in the open problems paper by Bowotsky, and he sort of sketched some proof ideas. I'll try to prove it a little bit using some without using the homotopy coniveau tower. So the statement is the zero slice of algebraic K-theory, KGL over a field, is motivic homology. So if you like, you can use this as some definition of motivic homology. Last time I did not define motivic homology properly. Anyhow, so this is the identification. And because we have this Bott periodicity for algebraic K-theory, so if we suspend KGL with P1, we get back KGL, then we have all the slices of K-theory. They are suspensions of the integral Allen-McLean spectrum. And then there's an extra statement. So if you insert some smooth scheme, the associated slice spectral sequence will have finite columns and converge strongly. This was proven by Bowotsky. And just for the topologists in the audience, the slices of KGL look just like the, say, even homotopic groups of the complex topological K-theory spectrum, KU. Okay. Yeah, so this answers Bailensen's question about algebraic K-theory. Here's a picture. So this is supposed to extend infinitely this diagonal.
Oliver, what was that word in the previous slide? There was a word I hadn't seen before, coniveau. What is that?
Oh, so this is Levine's notation for the filtration he defines, and this filtration is defined using cycles of a given codimension in a smooth variety, taking a product with some large affine space. So the coniveau refers to the codimension of cycles.
Okay, thank you.
Yeah, and I could, of course, I could try to say a bit more, but it's rather technical. I'd like to refer to Levine's papers for this. So he proves that the coniveau filtration that he describes on both S1 and P1 spectra actually coincides with the slice filtration, and this is a very powerful technical tool which can be used at least for certain spectra. And I will sketch a different proof of this theorem, which is sort of more topological in nature. Okay, let's see. Yeah, this was just a picture, and what you sort of then can already guess, once motivic homology is identified as a slice of something, the slice of it should be easily computed. So there's in some sense, easy statement about motivic homology that it vanishes in negative weights. And this means when you map a suspension spectrum of a smooth scheme into it, and you smash this with at least 1 GM, then it will map trivially to motivic homology. So the first effective cover, first effective cover of the Algebraic spectrum, that vanishes. And the more complicated statement is to show that motivic homology is actually an effective motivic spectrum. You know, once you have this, you get that both these two maps are isomorphisms. And there's one argument which works over a field of characteristics 0. You can use the Suslin-Nowotzki motivic Deutsch-Thom theorem, which expresses motivic homology using infinite symmetric products of spheres. And this can be used to show the effectivity of motivic homology. And then the question is what happens over fields of positive characteristic. And again, Mark Levine used his homotopic coniveau filtration to prove that for every field, the Algebraic spectrum over this field coincides with its zero slice. And this can in fact be generalized using Spitzweg's Algebraic spectrum over a Dedekind domain. This generalization is due to Tom Bachmann and Marc Hoyois. And yeah, again, this motivic homology then has a single non-zero slice, which it's the zero slice itself. This is the same as the homotopic groups of the topological Algebraic spectrum. So that again compares well. And now let's use the main technical tool for computing slices, algebraic Bordism, Nowotzki's motivic Thom spectrum. And I had these Lazare generators already on a slide on Tuesday. And what one can do is one can quotient out these generators, and the Hopkins-Morel theorem, which was properly documented by Marc Hoyois, says that the canonical map you then you get by using the canonical orientation on motivic homology. This induces an equivalence. So this is similar to the topological situation for MU, and this works over any field with the caveat that you have to invert the exponential characteristic. So exponential characteristic means it's 1 if the characteristic is 0, and it's the characteristic if the characteristic is positive. Yeah, so over field of characteristic 5, you have to invert 5, then you are sure that this map is equivalence. And let me sketch, or very briefly, give you some arguments of the proof. So the proof proceeds by proving that not the map itself, but once you smash it with the Algebraic spectrum, then it's an equivalence. And this fact splits into two parts: a rational part, which can be taken care of using motivic Landweber exactness, which is due to Nico Naumann, Markus Spitzweg, and Paul-Arne Östwer. And then there's some finite part, and for this argument you use various computations using the motivic Steenrod algebra to get a statement on homotopic groups. And since the spectra involved here are cellular, a result of Dagger and Isaacson gives us that this is then an actual equivalence of motivic spectra. And this homotopic group statement also involves that basically modules over an unbounded lane spectrum are the same as motives. So this sort of simplifies some arguments. And this works only if L is a prime, which is different from the exponential characteristic. So the problem is we don't really know how the dual Stinot algebra, the dual mod P Stinot algebra looks like over a field of characteristic P. And people are still working on this. Yeah, I just during lunch talked to Markus Spitzweck about this. He's still working on it. So stay tuned, it might happen. Okay, and then you can deduce that the actual map phi is an equivalence once you know that this quotient here is an HC local motivic spectrum. And for this, you look at the zeroth co-connective covers. So you truncate everything above 1 with respect to the homotopic T structure. And there's this computation is rather straightforward, that in both cases you get that the corresponding pi 0 is just Milnor K-theory and the canonical map here is an isomorphism. And then you can use the homotopy T structure truncations of this quotient to get the desired locality statement. And this uses this theorem I also had on one slide, which applies not only to the slice filtration, but also to other filtrations, so that everything is nicely multiplicative. Okay, and then let's draw some consequences. So assuming that this was now really a proof. So we get that the effectivity of motivic homology, at least after inverting the exponential characteristic, we get an identification of the zero slice of the sphere spectrum. There's an easy geometric argument that the zero slice of the sphere spectrum is the zero slice of MGL without inverting anything over any base. Yeah, we also get then, this is work of Spitzweck again, a computation of the higher slices of algebraic Bordism as an appropriate suspension of suitably many copies of the Allenberg-MacLane spectrum, and the degree Q part of the Lazar ring tells you how many copies you need. And in this situation, we actually get that the Qth filtration is the same as the, so the Q effective filtration is the same as the very Q effective filtration. So in this case, we already computed the very effective slices. They coincide with the slices. And the slices of MGL correspond to the topological homotopic groups of MU. Yeah, and just to emphasize, so the computation of the zero slice of the sphere, that this is the Allenberg-MacLane spectrum, this holds over a Dedekind domain and without inverting anything. Again, Bachmann-Hoyoa. And I'm going to be lazy and I might just skip inverting the exponential characteristic. And you're free to complain about this. Yeah, so this is meant as a further encouragement to interrupt the speaker in this electronic seminar. Shouldn't the characteristic be inverted is a question you can almost always ask. Let's see. So here's the picture where the slices here are sort of corresponding sums. So for the 2 slice, we have 2 plus brackets 2 suspension of HC, one generated by x1 squared and the other by x2, and yeah, this goes on according to the Lazar ring. Okay. So here's a quick sketch of the proof or of the computation of the slices of algebraic K-theory. So little KGL, this is defined as the very effective cover of uppercase KGL. And we have, let's say a Conner-Floyd theorem. So the orientation on Bott periodic KGL, the canonical one, gives you a map from MGL to KGL. Since MGL is very effective, this factors over the very effective cover, and one can then check that little KGL is actually a quotient of MGL by the Lazare generators X2, X3, and so on, just as in topology. And if you want to get the Bott periodic version, you have to invert X1. And from this, you get the computation of the slices that are already stated, but also that the qth effective filtration for KGL is the qth very effective filtration, and that it's just the zeroth very effective cover shifted around. So in some sense, the filtration is very simple in this case. And since the very effective filtration is a Hausdorff filtration, we get a convergence statement here. This is in some sense almost for free. So the homotopy limit of the qth effective covers is the same as the homotopy limit of the very Q effective covers, and this is contractible. Okay, let's this is sort of one possible approach to Bailensen's question. Let's now move on to the sphere and compute the slices of the sphere. And one way to do this, as suggested by Bowatsky in his Open Problems paper, is to use the MGL-based Adams resolution of the sphere spectrum, or I should probably say Adams-Novikov resolution. My apologies. And we have this diagram of which we can take the homotopy limit or the indexing category delta. And this induces a map of slices. So we can take the homotopy limit of the slices indexed over delta. And the induced map, this is an equivalence. This is the claim. And here's a proof. So look at this map for some motivic spectrum. And then observe if this motivic spectrum happens to be an MGL module, then you can sort of easily compute this homotopy limit because you have an extra map from MGL smash E back to E. Yeah, so in some sense, this Adams resolution splits. I don't know what the proper word for it is, but in this case, this property passes on to the slices, and then it's straightforward that this map is an equivalence for an MGL module. And then we look at the unit map for MGL, and we take its homotopy cofiber, MGL bar, and because we already know what happens on the level of the zero slice, so the zero slice of the sphere is the zero slice of MGL, so the zero slice of MGL bar is contractible, and this means that it's one effective. And then if we take smash powers of it, this is then going to be M effective, the M smash power. So if we have M big enough, bigger than Q, then on this map phi, both the source and the target are going to be contractible. So it's an equivalence. And then we use the fact that the slice functor is a triangulated functor. This is important now. And then you can use this homotopy cofiber sequence and downward induction. So this approach fails for the very effective slices, and as far as I know, there are not too many very effective slices known for the sphere spectrum. The zeroth has been computed by Tom Bachmann. I don't know about the first. Okay, so we get this computation here, the qth slice of the sphere spectrum. This is an appropriate suspension of motivic cohomology with the following coefficients. It's Z tensored with the sort of direct sum of the E2 page of the topological Adams-Novikov spectral sequence. So this is actually a finite sum for any fixed Q, and the groups inside there are finite abelian groups, except if both P and Q are 0, then it's just Z, and this is then just the 0 slice. And as an addendum, this will be convenient. Both sides have a canonical multiplicative structure. Yeah, if you view this as graded over Q passing through the integers, and the multiplicative structures are compatible. Okay, and to prove this theorem, of course, we use the lemma, which gives that the qth slice of the sphere spectrum is the homotopy limit of the qth slice of these iterated smash powers of MGL. And since we know what the what the slices of MGL are, and we have a description of the sort of the Landweber-Novikov, the dual Landweber-Novikov algebra, MGL, smash MGL, using the standard generators, we get that we can equally well use the homotopy limit of the following Einberg-MacLane spectra, where we use the topological homotopy groups of appropriate smash powers of MU. And then we can move out the sort of the Einberg-MacLane spectrum through this homotopy limit, because yeah, basically the chain complex this gives us here is it's a perfect chain complex, and then the homotopy limit corresponds to the total complex, and the homology groups of this total complex are the E2 page of the Adams-Novikov spectral sequence. And since the chain complex of abelian groups is quasi-isomorphic to its homology, this gives you the computation. So in some sense, it's rather straightforward. And yeah, this sort of says nothing about the multiplicative structure, you have to write down an appropriate diagram, and nothing goes wrong there. So the first statement is that the slices of the sphere do not compare well with the homotopy groups of the topological sphere spectrum, which, yeah, I guess is now an advantage because we have control over the slices here, maybe a bit more than over the homotopy groups, stable homotopy groups of topological spheres. And here's sort of borrowing knowledge from homotopy theorists like Zahler and Ravenel, we can explicitly write down a couple of slices. So here's a picture from Raphael Zahler's annals paper on the Adams-Novikov spectral sequence at the prime 2. I hope this is visible enough. And yeah, down here is the two primary part of the stable homotopy groups of spheres, and this here is what the E2 page says. And I guess what might have distracted a few people then is that there are quite a few differentials, unlike the Adams spectral sequence at the prime 2. There are less differentials, but actually these differentials they have to come up. You will see soon. Yeah, that's the picture. And when we now draw the picture for the slices of the motivic sphere spectrum, there's some kind of some linear transformation going on, which moves this diagonal to a vertical line. That's the following picture. Here you have, well, the zero slice is integral motivic homology, and then you have this tower of mod 2 motivic homologies. This tower here corresponds, so I'm going to be switch back and forth, corresponds to this diagonal line here. And then here we have, if you're sort of, if you want to distract yourself, you can count the little spikes here on the stars. These are 12. This is Z mod 12, which comes up in the integral Adams-Novikov spectral sequence. So here you see the Z mod 4. The 3' primary part is not visible on Zahler's table here. And you notice there are zeros here, and and it's this list of zeros here. And this goes on. I could go through all the columns here. This is a Z mod 240, Z mod 504 over here.
I don't see that many spikes. I don't see 240 spikes.
No, of course not. I ignored the 2 primary information here. These should be 15 spikes. And these should be, I think I ignored 3. Maybe these are 21. Yeah. It should be divisible by 7. So if you like, you can count. This should be a Z mod 6. Okay. Yeah, I apologize for this really childish drawing. I'm going to improve it by adding lots of indices as follows. So the standard naming convention in the Adams-Novikov spectral sequence, this gives us the alpha family, and this you see in this diagonal here, alpha 1, alpha 2, alpha 3, alpha 4, and so on. And then this tower here is really powers of alpha 1. And since alpha 1, alpha 2, this becomes 0, you have no tower here. But for alpha 3, you have a tower, alpha 1, alpha 3, alpha 1 squared, alpha 3, and so on. But we have this other element, this is alpha 2 squared. And this, there's also a better beta name for it, I guess. Maybe the naming here is not, it doesn't fit perfectly with the one in Ravenel's book, Complex Cobordism and Stable Homotopic Groups of Spheres. I think these alpha should really be, alpha 2 should be an alpha bar 2 over 2. I apologize for that. I wanted to simplify this a little.
So Oliver, like the horizontal lines in Adams-Novikov, like if you look at one filtration, Adams-Novikov filtration, those are going to correspond to diagonals of slope 1?
Yes.
Okay.
Yes. That's what's going to happen. Okay. Any further questions? Complaints about notation, number of spikes? Nothing? Okay, good. Then, these are just pictures for motivic spectra, and now let's look at the corresponding homotopic groups. And so for an integral motivic homology, I use sort of uppercase h, and mod 2 will be just lowercase h. And if there's like something like mod 12 or mod 240, this might be indicated by some appropriate subscript. And there's often the group Z mod 2 times Z mod 2 appearing. There will be the subscript 2, 2. And for later use, I already had tau there. This was the element -1 in little h01. And we also have the square class of -1 which is denoted rho usually. And if, for example, we look at pi k plus brackets 3 of the E1 page of the slice spectral sequence, then of course we start by looking at information from the 3 slice. So in the 3 slice you have 2 summons here, 3 plus brackets brackets 3 suspension and a 2 plus brackets 3 suspension. So you see the H00 here and the H00 here. They correspond. And what comes in from the 4 slice, so you have the fourfold, the fourfold GM suspension of mod 2 motivic homology. This gives you already 2 groups on the E1 page. And for the 5 slice, this then gives you 3 groups here. Yeah, these 3 all come from this single dot, because we have this simplicial degree to vary around. But fortunately for motivic homology with finite coefficients, there are no negative simplicial degrees. Yeah, the corresponding groups will be 0. This is still unclear for integral coefficients. I'll mention this soon. Okay, so this is how this picture of slices translates to a picture of actual groups when you want to determine some actual groups. And of course you can vary the weight. If we, for example, look at pi k plus round brackets 2, then already the 2 slice will play a role, and we see some mod 12 information coming in here. And so on the previous slide, it started with stuff coming from the 3 slice, which gave us just 1 group here, but now we have 2 groups here and another 2 groups here. Yeah, you can sort of guess from this how the pattern goes, and if you want, you can, yeah, maybe it's worthwhile stopping here where the first integral group appears when we look at pi k plus brackets 0. So what you see here in this 0th column then is the associated graded for the fundamental ideal filtration on the Grothendieck ring. So this looks like the Grothendieck ring. And yeah, on the previous page you can see the associated graded for the fundamental ideal filtration on the Wittring. This here looks like the Wittring. Okay, and the general picture is then a bit uglier, because these groups may extend along a horizontal line. And for example, for integral motivic homology, it might go on to negative simplicial degrees. I mean, this is the Beilinson-Soulé vanishing conjecture, that integral motivic homology with negative simplicial degrees, that this vanishes. This is unclear. It's still open. It's known for number fields and finite fields and probably function fields over finite fields. Yeah, I'm not sure. I haven't checked the status there. So there are a couple of groups coming up, and we want to erase some of them so that we can actually get our hands on concrete computations. So we have to understand at least the first differential a bit better, and in order to do so, one weapon of choice is Hermitian K-theory. And this forces me currently, at least, to restrict to fields of characteristic mod 2, because only then we have a representing spectrum, which was constructed by Jens Hornbostel. And so the Q stands for quadratic, because it classifies vector bundles with a quadratic form on them. And again, I would like to list similarities with the topological situation. So Hermitian K-theory behaves to algebraic K-theory as real topological K-theory to complex topological K-theory. So you can think of algebraic K-theory as the cone on multiplying with the Hopf map on Hermitian K-theory. And the maps that come up there are then the forgetful map, so you forget quadratic forms and only keep the vector bundles. And if you have just a vector bundle, you get the associated hyperbolic space from it. You take a direct sum of the vector bundle with its dual, and then there's a canonical hyperbolic form. This gives you the other map. And basically, this information allows you to determine the slices, starting from the slices of algebraic K-theory. So this is a theorem I proved with Pollard and Östwer. The slices of Hermitian K-theory over a field are given by infinite direct sums of Allenberg-MacLane spectra. For the even slices, we have some integral contribution. Otherwise, it's only mod 2 contribution. So these are infinite, and in particular, this does not compare well with the homotopic groups of the topological real K-theory spectrum. Yeah, here's the picture. You have these integral guys, and then you have these extending to the left-hand side sums of mod 2 Allenberg-MacLane spectrum. So that looks pretty large, and we will shrink this a bit by taking a very effective cover soon. But the periodicity that KQ has simplifies the determination of the first slice differential. So let's pass on to that. So I already record the first slice differential can be viewed as a map of motivic spectra. And in all the examples you've seen, the slices are sums of motivic Allenberg-MacLane spectra. So it's interesting to know possible maps between motivic Allenberg-MacLane spectra. In this case, the first differential will be a map raising the weight by 1. But Wołodzki computed basically, he computed all endomorphisms of motivic homology with primary coefficients over characteristic 0 fields. And this was extended by Hoyoa, Kelly, Östwer to positive characteristic fields as long as you stay away from the characteristic of the base field. And Markus Spitzweg extended this to Dedekind rings once you again have the prime that you're interested in to be invertible. So this will be so not the whole Steenrod algebra, but at least or at most the weight 2 part. This will be interesting for the first differential. And here's one first computation of a slice differential for mod 2 algebraic K-theory. And since the slices are triangulated, the slices are just mod 2 Allenberg-MacLane spectra. And then you use spot periodicity to conclude that you basically only have one differential. They are all the same up to some appropriate suspension. And what you then get is an operation of which there are only 4 possible types by Wołodzki's computation of the motivic Steenrod algebra, namely either 0, square 2, square 1, square 1, square 2, or the sum of the latter 2. And motivic, the thing is, this here is supposed to be a differential, so it should square to 0, and the motivic Ardem relations tell you that there are only 2 choices left. Either this differential is 0, or it's the first Milnor operation, square 2, square 1 plus square 1, square 2. And fortunately, Suslin computed mod 2 algebraic K-theory of the real numbers, and this tells you, using the convergence statement, that the non-zero, that the differential has to be non-zero. So that's the one. And you can sort of base change from spec Z, where 2 is inverted, to get this computation over any field of characteristic not 2. And using the knowledge of this differential here, we have the first foothold for the differential on Hermitian K-theory. If we restrict it to the integral summand, it has to be passing to mod 2 coefficients and then a square 2. So in the picture, this gives us this little green arrow here, which is sort of a visualization of the differential. But now you can use the periodicity properties of Hermitian K-theory to get that this here has to extend, and also on every fourth part here. And now again, you wonder, is this all? And it cannot be all, because, for example, if you compose 2 square 2's, this is by an motivic idem relation tau square 3 square 1 and not 0. But differentials have to square to 0, so there have to be more operations coming in. So just by idem relations, you get this whole zoo of multiplications with tau and square 3 square 1's. Yeah, and in case there's some integral cohomology involved, you have the corresponding boundary map from mod 2 to integer coefficients involved, or sometimes you have to project to mod 2 coefficients first. So, but what you get then is that here on these sort of other columns, we have first tau, then square 3 square 1, which again is not 0. So you have to have even more, and this gives us these towers here, which are given by square 2 plus rho square 1. So this is the description of the first slice differential for Hermitian K-theory. And in order to move this to the sphere, it suffices to look at the very effective cover of Hermitian K-theory, little kq. That's the notation. And you still have a Wood co-fiber sequence. So the cone on multiplication with the Hopf map on little kq, this is then little kgl, as in topology. And since we're taking a very effective cover here, determining the slices, then this is not so hard. And we get the following picture of the first slice differential for little kq. So this was written down in a paper by Alexei Ananievsky and Paulana Öster and myself. It's basically the picture you see here, but you throw away the negative stuff. So we have something smaller and more manageable. And in order to get to the sphere, we now have to look at the unit map from the sphere spectrum to little kq. And there's the following lemma, which maybe looks a bit overwhelming. And this lemma tells you what the unit map does on the alpha family. So it's some kind of, I shouldn't really say this. It looks like some kind of image of J argument, but basically it's just using the previous argument, sort of the differential for algebraic K-theory, passage to algebraic K-theory. This already tells you that certain maps on slices have to be non-trivial. And yeah, it's non-trivial in such a way that you see the what do I have to say, the odd index alpha family, alpha 1, alpha 3, alpha 5, and alpha 1 multiples of these. So you get the following enhancement of the picture of the slices of the spheres, where you have now these green arrows coming from Hermitian K-theory. You have the red arrows, this is multiplication with tau, coming from Hermitian K-theory. You have the square 3, square 1. And I guess, yeah, the previous lemma also tells you that something has to go on here on this diagonal, coming from the alpha family. And it's not entirely clear what sort of the first and third and fifth arrow and so on the diagonal are, but the blue ones here are, you have some connecting homomorphism from whatever group you have, Z mod 12 to Z mod 2, and then a square 2. So this is the second and the fourth and so on. And yeah, and we already know this here. And if one works a bit harder and uses the multiplicative structure, one can determine the whole diagonal here involving all the little stars with their spikes. And what you see here is sufficient already for the pi1 computation for the sphere, but of course you can use Adem relations to get that certain maps are 0 actually. So these arrows shouldn't be here. This is just for emphasizing that there might be lots of non-zero arrows here where we don't really know what's going to happen, but now we have actually zeros. And if we like, we can also compare with topology, which detects multiplications with tau. So the new non-zero map we get here is this one and this one. So these red arrows that you see here, they correspond to the arrows in Zahler's picture of the Adams-Novikov spectral sequence. So I don't know whether you're going to be dizzy now, but I'm going to flip through the pages and see that I get to Zahler's picture. Where is it? Oh, I'm sorry. Yeah, all these arrows here, they correspond to multiplication with tau in the slice spectral sequence. Where are we? Yeah. Okay. So this allows us in some very limited range to compute the E2 page, and we see the sort of the zeroth column still persists and tries to compute the nth Milnovich K-theory. That's fine, that fits with Morel's theorem. And now what happens is that this the column for pi1 and the column for pi2, they become finite. And this, of course, also simplifies the computation, because when we want to compute the E infinity page, there are only finitely many differentials we have to worry about. This is in general not clear, because in general we have these infinite towers. You can see it here for pi0. This is an infinite tower, and it has to be there because the fundamental ideal filtration on the Witt ring in general is infinite. So for a formally real field, for example. Yeah, let's see. So basically what is written there is just you take quotients and some kernels with respect to the differential that I've given before, and that these columns turn out to be 0. This uses one property of mod 2 motivic homology, which was proven by Wowodzki. So I won't go through all the stuff with the higher differentials. I'll just want to mention the Milnor conjecture on Galois homology as proven by Wowodzki. This gives us that multiplication with tau on mod 2 motivic homology is an isomorphism whenever this makes sense. So in this range here. So this tells us when we have an element in mod2 motivic homology with this by degree s comma w, we can write it as an appropriate power of tau, and then something which comes from actually mod2 Milnor K-theory. And this will be very convenient. So let me just switch back to the differential. We have all these tau parts of the differential, and they will induce surjective maps. And these surjective maps, sort of coming from this second column here, they will hit all the groups that are here on the E1 page, on the pi1 column, and also here on above 3, and in the pi2 column above 4. And this ensures that these columns are finite. Okay, maybe this is a good point to stop and have a minute for questions maybe. And next time on Tuesday, I can then continue and show that this is actually the E infinity page, and then also show that we indeed computed something which has to do with the homotopic groups of spheres.
Okay, I'm going to unmute everyone, so we first of all thank him. Okay, and we have some time for questions. Actually, I'm going to mute everyone again to cut down on the background noise. And, okay, questions?
I have a question. Is there a general idea of when the effective and very effective slices agree? Does it look like they agreed for like complex orientable spectra?
So what Markus Spitzbeck proved is that he basically determined the slices of Landweber exact spectra, motivic spectra. So for these, the two filtrations coincide.
Okay. Is there a way of moving between the two when you're not Landweber exact?
Well, so I guess one interesting work to look at is, for example, Tom Bachmann's computation of the very effective slices of Hermitian K-theory. I mean, this sort of indicates how the very effective slices, you can think of these as a conglomerate of the usual slices. And in fact, the very effective slices of Hermitian K-theory, they just look in some sense like the homotopic groups of real topological K-theory.
Right.
So in some sense, they are very finite, and they subsume this infinite sums that I had on one slide. So of course there is a relation, but for example, there is no easy way to guess what the very effective, say, 1 or 2 slices of the sphere are from the description of the effective slices.
I see. Thanks.
Okay, other questions? Well, I had kind of a question or speculation or something. So, you know, Adams-Novikov spectral sequence is complicated to begin with, which means that like the slice E1 page is at least as complicated as that, right? So, but there's of course this regular structure that occurs with the alpha i's and also the alpha 1 multiples, right? So,
yeah.
Do you think, like, let's say you just ignore everything except for the alpha i's and their alpha 1 multiples. Do you think that like you could go further? Is there more, like, can you be more specific with the computations, or are already like the difficulties that you're running into sort of already showing up with sort of within those, you know, within those alpha elements?
So my guess is that we have a rather good grip on the alpha family.
Okay.
But already sort of dealing with the multiplicative structure there is already a bit more it's a bit tricky. So Glenn Wilson did some work there, some impressive work. Yeah, and yeah, from my point of view, there's a lot to do in order to pass to the higher filtrations. So to me, the picture is not clear yet. Work has to be done.
Okay, any other questions? Okay, if not, I'll unmute everyone so we can thank him one more time. And we will meet again next week, next Tuesday, 5 days from today, for the third and final part of Oliver's mini course. Okay, thanks everyone.